Today we're going to go over small signal operation, differential amplifiers, and play around with them a bit. So let's say that we have a differential amplifier. Where we have some resistance RD. We're going to apply some voltage VN1, transistor M1. Our tail current source IREF. And on the opposite side, we have a similar network. This guy over here, VN2. Here is transistor M2. Here's V out 1. Here is V out 2. Bless you. So let's call VN1 a combination of two signals. A common mode DC voltage and 1/2 of some small signal differential mode voltage, and VN2 will split up as well. We have our common mode voltage, which establishes our biasing point, and we're going to have minus 1/2 times our small signal differential mode voltage. So what the common mode portion does is it establishes some current ID1 flowing through transistor M1, and similarly some current ID2 flowing through transistor M2, and with the constraint that our resistors RD are identical and our transistors M1 and M2 are matched, we could see that V out 1 in this case would be VDD minus 1/2 IREF RD, and then plus what I'm going to call VODM1, and V out 2 will be VDD minus 1/2 IREF RD plus VODM2. There's going to be some small differential mode voltage at the output, but effectively the whole thing is going to be biased at this DC level. Okay. So if we look at this guy at the small signal level, we're going to have something that looks like this. Here's our transistor RD, excuse me, our resistor RD. Here is GM1, VGS1. Here's ROut1. Here's our small signal voltage, VOD1. Here's our input. And this would then be VGS1, which makes this gate, this drain, this source of transistor 1. And on the right-hand side, we're going to have effectively the exact same thing, but mirrored. RF2, GM2, VGS2, VODM2, RD, -1/2, VIDM. This guy is VGS2. So this means that we have gate 2, drain 2, source 2. And I'm going to call this nodal voltage right here Vx. So we have some voltage Vx here, which may be non-zero, because the small signal model for our current source is an open circuit. So to understand what's going on with this guy, we have to figure out what's going on with Vx. All right. So I have this ginormous small signal model. So what I can do is I can express by doing Kirchhoff's voltage law and recognizing that Vx is a nodal voltage with respect to ground. I can apply Kirchhoff's voltage law to the input side of both of my transistors. And so what I'll find, so if I do it around this loop that I'm about to draw here, go around this side to ground, that's going to be one of them. And then I'll go here to ground, and this will give me a second equation. So VL at the right-hand side gives me -1/2 VIDM plus VGS1 plus Vx is equal to 0, or VGS1 is equal to 1/2 VIDM minus Vx. And if I do, sorry, that should have been the left-hand side, not the right-hand side. My apologies. If I do the same thing on the right-hand side, I have negative, which is going to look like positive 1/2 VIDM plus VGS2 plus Vx is equal to 0. which is going to give me VGS2 is equal to negative 1/2 VIDM minus Vx. So before we do this next step, we are going to make an assumption here. And that assumption is that our transistors are matched. So if RD are identical resistors, and M1 and M2 are identical transistors, then we should see that GM1 is equal to GM2. So let's just call that GM. And we should see that ROUT1 is equal to ROUT2. Let's just call that die ROUT. And so I'm going to apply Kirchhoff's current law at node X. So I'm going to say that I have this current flowing into node X, this current flowing into node X, this current flowing into node X, and this current flowing into node X. And so what that gives me is GM times VGS1, which we know to be 1/2 EIDM minus Vx plus VODM 1 minus Vx divided by ROUT plus VODM2 minus Vx divided by ROUT plus GM times VGS2, so negative 1/2 VIDM minus Vx. All of this together looks like 0. Is everybody okay with this thus far? Okay. So I can lump together some like terms and all that kind of stuff. But the first thing that we can observe is that we have a factor of GM times 1/2 VIDM right here. And then we have a factor of negative GM times 1/2 VIDM on the right-hand side. And so those two guys cancel each other out. So this guy goes away when those two bits get added together. And so what I am left with, so let's see, how am I going to do this? I would have VODM 1 plus VODM2 minus twice Vx divided by ROUT minus 2 GMVx is equal to 0. If I did my algebra correctly, and I think I did. So all I did was add this guy and this guy, my differential mode output voltages together, making that term in the parentheses. And then there's 2 contributions of negative Vx over R out, and then there's 2 contributions of exactly negative GMVx. All right, so the next thing I'm going to do is I'm going to apply Kirchhoff's current law at my output nodes here. And so let's do this guy first. So I'll say that this current plus this current plus this current are going to add together. And on the other side, I'm going to have this current plus this current plus this current sum together to make 0. So KCL at BODM1 looks like BODM1 divided by RD plus GM times 1/2 VIDM minus VX plus BODM1 minus VX divided by R out is equal to 0. And I do KCL at my other output node, I get effectively the exact same equation, except all my BODM1s become BODM2. And I have to remember to change my sign on my input differential mode voltage. So what I'm about to do next is similar to what we did introducing the concept of a supernode way back in circuits 1, where I can say that 0 plus 0 is equal to 0. So lump those guys together. And I get BODM1 plus BODM2 divided by RD plus GM times 1/2 VIDM minus 1/2 VIDM minus twice VX plus BODM1 plus BODM2 minus twice VX all over R out is equal to 0. And again, we can see that our input differential mode voltage contributions wind up canceling each other out. And with a little bit of algebraic manipulation, this winds up giving me BODM1 plus BODM2 multiplied by a factor of 1 over RD plus 1 over R out is equal to 2 VMVX plus 2VX over R out. And finally, if I divide through by that 1 plus RD, 1 over RD plus 1 over R out, that's the same as multiplying the right-hand side by those two resistances in parallel. Everybody okay with that? So that leaves me with BODM1 plus BODM2 is equal to twice GM Vx plus twice Vx over R out, multiplied by a factor of RD in parallel R out. We'll call this guy equation 2. And this guy up here, equation 1. And now I'm going to substitute equation 2 into equation 1. And so what I'll wind up having is two GM Vx plus twice Vx over R out times RD in parallel with R out so let's see, that's my VODM bit from up here. Sorry, let me look at it. Minus 2Vx. This whole thing over R out. And then minus 2 GMVx. And from this guy, I have a single equation only in terms of Vx. So what does Vx have to be? It has to be 0, right? Because every single term has a Vx component. So a whole bunch of stuff multiplied by Vx equals 0 means Vx has to be 0. So this means that even though we have a differential mode signal providing skewing currents in different directions, we wind up seeing that our source node for both of our transistors looks like an AC ground, which makes analyzing our circuit very easy, right? So with sources of both of our transistors tied to ground, we have something that looks like this. RD. We're at 1. Here's VODM1. One half VIDM plus minus VGS1. And over here on the right hand side, excuse me, this is GMVGS1. We have effectively the same circuit. R out 2, VODM2. GMVGS2. GS2, negative 1/2 VIDM. All right, so I'm gonna line down the middle here. So the left-hand side of the circuit looks exactly identical to the right-hand side of the circuit, except that they have different input voltages being applied, right? So it stands to reason that if we can figure out how the output voltage of the left-hand side behaves due to its corresponding input voltage, we can apply the same techniques to figure out what's going on the right-hand side here. So what kind of amplifier does just one side of this thing look like? Well, it's the exact same kind of amplifier that we constructed this thing with, right? It's just a simple common source amplifier, okay? So it's a common source amplifier being loaded with a resistor RD, and we have not neglected channel length modulation. So for that, we should be able to say that VODM1 is simply the gain of a common source amplifier, which in this case would be negative GM multiplied by R out in parallel with RD multiplied by our input signal 1/2 VIDM. And similarly, VODM2 is equal to negative GM times R out in parallel with RD times negative 1/2 VIDM. And I want to scroll up here for just a minute, right? So we figured out what this bit is here and what this bit is here. If we were to take this difference and call that V out, what would happen? So let me essentially rephrase my question here. Our output voltage at either of our output pins have some DC offset that depends on the biasing conditions of our circuit, right? Actually, they kind of don't. Assuming that the common mode signal is common to both sides, this guy is independent of what our DC biasing is, right? So we have DC offset plus this output differential mode voltage minus the DC offset that is the same minus this differential mode voltage. We get rid of all of our output common mode signal, right? So the common mode signal gets completely rejected, and we wind up finding out that, sorry, let me scroll here. Our output voltage is just negative GM R out in parallel with RD times our total input differential mode signal. Right? So we take either of our inputs, or excuse me, either of our outputs with respect to ground, we wind up carrying through that DC offset at the output. But when we take the output with as a difference with respect to each other, the DC bit gets thrown away, and all we see at the output of our circuit is the amplified differential mode signal, right? So that's pretty dang useful. One problem with this is that the gain is limited by our choice of RD, right? So for a MOSFET transistor, our output resistance, R out, is usually on the order of tens of kilo ohms, but the size of RD directly influences whether or not we can keep both of these transistors in the saturation mode region of operation, right? So it's typically going to be smaller than the output resistance of our transistors, which means this guy is going to be approximately negative GM RD times our full differential mode input voltage signal. So how might we go about boosting that gain? Any thoughts? So how can we increase RD without increasing RD? And so what I mean by that, I know that sounds weird, right? We need to figure out a way to increase the resistance seen. We need to figure out a way to increase RD, the small signal level, without increasing it at the large signal level, right? Because increasing it at the large signal level can push our transistors out of saturation and into triode. So how have we done that before? So that's one way to do it, and we'll talk about that in a minute. The first way would be if we bias this guy with PMOS current sources first. So if we replace the resistors RD with PMOS current sources like this, all right? So this guy M1, this guy M2, this guy M3. Actually, let me turn that guy around. And I'll explain why in just a second. So this guy down here is IREF. I'm going to tie the gates of these guys together and just call this V bias. V out 1, V out 2, here's V in 1, and here's V in 2. So if I tie the gates of those two transistors together, then VSG3 and VSG4 are identical. which means this current ID3 has to be equal to this current ID4. And therefore, R out 3 has to be equal to R out 4. We can just call R out P. Right? So tying those gates together, make those transistors have the same drain current, which means they have to have the same transconductance and the same output resistance. So let me go back to this guy from a couple minutes ago, right? So what we had here, what we found our gain to be effectively was negative GM times the output resistance we saw looking in, right? Where it was just what we saw up in parallel with what we saw down. So without doing a ton of extra work here, all we've done is replace those resistors with transistors. So what we saw looking down should stay exactly the same. What are we going to see when we look up? So if we drew our small signal model for just the PMOS side of this guy, we would have our source up here. This would be GM, I'm going to call it GMP, VSG1. Here's our resistance R out P. This is the source of transistor 3. This is VSG3. This is the drain of transistor 3. And over here is the gate of transistor 3. So where should our gate of transistor 3 be at for small signal? Ground. So that means VSG3 is what? 0, which means the source doesn't provide any current. And so all we see looking in through that drain terminal is just R out P. So for this particular configuration, we have, our gain is still going to be negative GMN in this case, multiplied by the resistance R out that we see, or that's just going to be negative GMN R out N in parallel with R out. So we've made let's see. So we've made RD look bigger on a small signal level, which is going to increase our overall voltage gain. And it's probably going to actually increase the amount of common mode voltage that we can have, because now we would see that our DC output voltage, so V out DC, this would be valid for 1 or 2. So let's see here. Actually, I don't want to say it. I was about to say that it should be VDD minus VSG3, but that's not quite true, because there might be a drain source voltage in our PMOS transistors to accommodate the amount of current that's flowing through. So I'm going to erase that, and I'm just going to say we would expect this to give us a little bit more headroom to deal with, right? So we could take this one step further by cascoding things as well. That's actually it's gonna give us a lot more gain if we cascoded things, right? So let's just write this down here. If we cascoded M1, 2, and cascoded M3 and 4, what would wind up happening? The output resistance looking down would be GM times R out N squared. Or excuse me, yeah. And the output resistance looking up would be GMP times R out P squared, right? So we would get a boost, but we'd also have to increase the complexity of our circuit by providing 3 bias voltages as opposed to just the one of them, right? Because we'd have to bias both of the transistors in our PMOS cascode and the top transistor in our NMOS cascode, which is going to crunch our common mode range that we can actually use, because we're going to have it fall between the bias voltage for the NMOS, or the highest bias voltage for the NMOS and the lowest bias voltage for the PMOS. So that's absolutely something that could be done to get more gain out of it, but there's a pretty significant trade-off in doing that. When we talk about telescopic op amps, which will hopefully be later this week, we'll talk about those trade-offs again. So this NMOS on bottom, PMOS on top scheme does a pretty good job of getting us higher voltage gain and a good amount of headroom. The biggest drawback of it is that we still have a differential mode output. So we would find it hard to use this particular configuration to drive a component, like a resistive load or something like that, okay? So the next thing that I want to talk about is effectively the single stage op amp. More officially, we will call it a differential pair with a current mirror load. So the last example had a current source load. Now we're going to have a current mirror load. And I'm going to put AKA single op amp. My goal for today is for us to talk about qualitatively how this guy works, and then get into the specifics of why it works that way on Wednesday. So let's consider the following circuit. It's going to be nearly identical to what we just had, except for one very specific change. So we have M1 and M2 loaded with PMOS transistors, M3 and M4, and our gates are tied together. But instead of us applying a fixed bias voltage, we tie the gate and drain of M3 together, which means our bias voltage occurs through that feedback loop, exactly like what happens with a current mirror, because this is exactly an NMOS differential pair being loaded with a PMOS current mirror. Now, one drawback of this approach is that our circuit is no longer perfectly balanced like we had before, okay? We wind up getting a single-ended output out of this system that provides us, so that's a single-ended output. But by that, I mean we only have one output node that we have to worry about. Output voltage is measured with respect to ground as opposed to measured with respect to another terminal voltage in our system. And it turns out that we get almost the amount of gain with this configuration as we got by loading it with current sources, except that now we don't have that negative factor out front. So it's practically identical from a gain standpoint, except that it's no longer an inverting amplifier, which is what we would expect with a common source stage providing the amplification. Okay. So let's look at this guy from a large signal perspective first. And we're going to make some very specific assumptions here. M1 and M2 are matched. M3 and M4 are matched. And we're going to ignore the effects of channel length modulation for our qualitative analysis here. Okay. So let's say that VN1 is equal to VN2 such that we only have some common mode signal being applied to this guy. All right. In that case, this voltage, VGS1, and this voltage, VGS2 are identical, right? We apply the same input voltage to both the input terminals. We wind up seeing that VGS1 is exactly equal to VGS2. Transistor M1 and transistor M2 have to be carrying the same amount of current, and that would be a current of I reference over 2. So what transistor M1 is doing is it's playing the role of the current source that is biasing that PMOS current mirror. Okay, so that means that M3 has to be carrying exactly I ref over 2 as well. Since M3 is carrying a current of I ref over 2, it's going to cause a voltage VSG3 to appear across transistor M3, and since the gates of M3 and M4 are tied together, the voltage of VSG4 must be occurring across transistor M4, which means our mirroring is achieved, and we see a current of I ref over 2 flowing through transistor M4 as well. Okay. So to recap what's going on here, since VGS1 and VGS2 are identical, the current I ref gets cut in half, with each transistor M1 and M2 carrying exactly half. M1 is acting as a current source, which is biasing M3. So it's forcing a current of I ref over 2 to flow through M3. And then we observe that current mirroring happens, which forces a current of I ref over 2 to flow through transistor M4. And we wind up seeing that the overall current that could flow out to a load is 0 amps, which is exactly what we should expect here. So effectively, we're not going to have any current losses or anything like that. So we're going to see that we reject large signal common mode, or excuse me, we reject large scale common mode signals extraordinarily well. Should have a very, very high common mode rejection ratio for this guy. All right. At the small signal level, using these same assumptions, let's look at what happens for a common mode signal. All right. So this is going to be GMP VSG3. And because we are ignoring channel length modulation, let's see. So this is going to be our source for transistor 3. This is going to be our drain for transistor 3. And no, I should have drawn it that way, yeah. And then this is going to be VSG3 here. So this is obviously the gate of transistor M3. Ignoring channel length modulation means we don't see that resistance between the source and the drain of transistor M3. While I'm at it, we'll draw up here what's going on for M4. GMP VSG4. So this is the source of transistor M4. Here's our drain of transistor 4. And this should be VSG4. Because the gate and drain of M3 are tied together, that's going to give us that, which means our small signal VGS3 and our small signal VGS4 are identical. Now let's get down here to the NMOS portion of things. So here we're going to have GMN VGS1. Plus minus VGS1. Here is some input voltage VCM. And then the same thing over here. Here's GMN VGS2. Put that on the other side. That's all one big node. And here is V2. This is that same differential mode input common mode signal, or small signal input common mode signal. All right, so, and then obviously, let's see, so this is the gate of 1. This is drain of 1. This is the drain of 2, the gate of 2, source of 1, and the source of 2. All right. And then the drains are connected together. So this is a rough sketch of our small signal system here. All right. So if we have some common mode voltage applied at the gate of M1, we are going to have some current. I'm going to call it lowercase I because it's a small signal current, is going to flow through transistor M1. Okay. That exact same current I must be flowing through transistor M3 because it's the only path. Similarly, input common signal applied at the gate of transistor generates a current, and it will also be I if our transistors are matched and we're applying the same input signal. This is going to draw the exact same current I through transistor M4. Now, this node that I've labeled here, D4, is our small signal output node, right? So the drain of transistor, or where the drain of transistor M4 and the drain of transistor M2 are connected is where we take our output voltage. So that means that, again, we have exactly 0 amps of current that could flow out through a load. So we have both large signal common mode rejection and small signal common mode rejection, which is fantastic. Now, a reasonable question would be, where the hell does all this current go? It's getting sunk by the current source, right? That's still connected. We just don't see it as a small signal. So we could treat it, if our current source had some finite impedance, we would see that exactly 2I winds up getting sunk through here. All right, so we have an understanding qualitatively of what the heck is going on here when we apply a common mode signal. So what if we change this guy and apply a differential mode signal? Is our small signal model going to change at all? No, the only thing that changes is our input quantities, right? So let me make a copy of this. And we'll tuck it in right here. I'm going to erase all these I's. Again, we're going to go over this and how it behaves in much more detail on Wednesday. So let's say that we apply positive 1/2 VIDM here and negative, my thing will write, 1/2 VIDM here. We would expect to see that small signal current I flowing through transistor M1. That same small signal current I flowing through transistor M3 because it's its only path. Since VSG3 and VSG4 are the same voltage, that same small signal current I will flow through transistor M4. But now we got a little bit of a pickle, right? If we apply positive 1/2 VIDM, we would see that we'd have a current of I flowing down through M2. Well, when we flip the polarity of the voltage, that's going to cause I to flow in the opposite direction, which means we wind up having twice I flow out through the output node, assuming it's connected to something that can allow that to happen. This is the beauty and genius of this scheme, right? It's this twice I that lets us get twice the gain of one of these single common source amplifier stages, right? So it's how we get the same gain as the double-ended output, even though we only have a single-ended system, okay? And we'll get into the ludicrous amount of math that makes that work on Wednesday, all right, as an introduction to real deal op-amp analysis. All right, any questions from today?